DuckDB under the hood, Module 6. One query, same data, but 1,000 times faster. Sorting 60 million rows by early order key takes about 3 seconds, but adding a limit of 10 to the same query takes under 1/10 of a second. Same rows, same column, different operator. This module explains why. DuckDB under the hood, Module 6. A comparison-based sort like merge sort asks, is A bigger than B? Over and over. That costs O of n log n comparisons. Radix sort takes a different path. It makes 8 passes over the data, 1 byte at a time. In each pass, it distributes rows into 256 buckets based on that byte, then collects them back in order. No element is ever directly compared to another. After 8 passes, the 60 million rows are fully sorted. The complexity is O of n times k, where k is the key width in bytes. For int64, that is 8. This is why early order key sorts so much faster than a varchar column of similar cardinality. DuckDB does the same thing with bytes. It makes 8 passes over the data, 1 byte at a time. In each pass, it distributes rows into 256 buckets based on that byte. 256 because a single byte takes values from 0 to 255, then collects them back in order. No element is ever directly compared to another. After 8 passes, the 60 million rows are fully sorted. The complexity is O of n times k, where k is the key width in bytes. For int64, that is 8. This is why all order key sorts so much faster than a varchar column of similar cardinality. Variable width keys like varchar cannot use Radix sort, so DuckDB falls back to a comparison-based sort for those. Here's how two-phase sort works, using local runs and then a k-way merge. In phase 1, each thread sorts its assigned morsels into local sorted runs. Morsels are around 120,000 row chunks, using the same parallelism model as aggregation. Phase 2 uses a k-way merge to combine all local runs into a global sorted output. Sorted runs live in paged data structures, and the buffer pool manages spilling to disk. There is no shared sort state during phase 1, so threads work independently. Here's how DuckDB skips the full sort when limit is small. When you use order by plus limit, DuckDB uses the top n operator, not order by. Each thread maintains a local heap of k elements. The database never materializes all rows in sorted order, so the heap stays small. Memory is O of k, not O of n, so there's no spill risk for small k. The explain command shows top n instead of order by. First, attach the TPCH scale factor 10 database in read-only mode. Now you can query the memory usage. This query selects the tag and memory usage in bytes from DuckDB memory. It filters for entries where memory usage is greater than 0. This gives us a baseline of DuckDB's memory usage before running any queries. Full sort, no limit. Let me run explain and see what operator the planner picks. The scan reads L order key and line number, just the 2 columns you asked for. Above it is the order by operator. Because there is no limit, DuckDB must produce all rows in sorted order. That requires materializing the full result before returning anything. DuckDB uses Radix sort, a pass-based sort that works column by column through the sort key's bytes, moving data into partitions that are then individually sorted. For 60 million rows, it will consume several hundred megabytes. If that exceeds the memory limit, it spills sorted runs to disk and merges them on the way back. Here's a query that orders the line item table by L order key. It then limits the output to the first 5 rows. You can see the first 5 L order key and line number values. Next, we'll look at how DuckDB optimizes this query using the top K optimization. Same query, but now with limit 10. Watch the operator change. The scan still reads all 60 million rows. There is no way to skip them without an index on L order key. But above the scan, DuckDB replaced order by with top n. This operator maintains a min heap of exactly 10 elements. As each row arrives from the scan, it is compared against the largest element in the heap. If it is smaller, it replaces it. Otherwise, it is discarded. The heap never grows beyond 10 entries. No full sort runs, no spill to disk. The result falls out when the scan is exhausted. 60 million comparisons against a 10-element heap, and the sorted top 10 appears. Here, we select L order key and line number from the line item table. We order the results by L order key. Then we limit the output to the top 10 rows. This gives us the 10 smallest L order key values and their corresponding line number values. Limit 100 instead of 10, still top n, but let me run explain analyze to see the actual timing. The scan reads all 60 million rows. The timing shown here is the actual elapsed time from explain analyze, not an estimate. The top n operator above it maintains a heap of 100 elements instead of 10. The operator overhead scales slightly with heap size, but the dominant cost is still the scan. The heap stays bounded regardless of how many rows pass through it. Watch what happens when the limit equals the full row count. That is the exercise. This query shows DuckDB's internal memory usage. We select the tag, the memory used, and any temporary disk storage. Notice only the base table is resident and temporary storage is 0. Those order by queries use top n, not a full sort, so nothing ever spilled to disk. Now we set a tight memory limit, just 64 megabytes. This caps how much memory DuckDB can use for the query that follows. Here's an order by with a limit of 5. Even under that tight 64 megabyte cap, it returns instantly. DuckDB uses top n. It keeps just a small heap of the 5 smallest keys as it scans. So it never sorts the whole table and never needs to spill. We check memory one more time. Temporary storage is still 0, nothing spilled to disk. The top n heap is tiny, so it fits easily within the 64 megabyte limit. A full sort that overflowed that limit would spill instead, and that's the story these next slides tell. Spilling a sort can be transparent via paged data. Sorted runs are stored in the same paged intermediate structures as group by. The buffer pool evicts cold run pages to disk, and the sort operator never calls spill. A full sort of 60 million early order key values at 64 megabytes memory limit guarantees a spill. Temporary storage bytes in DuckDB memory shows how much hit disk. Top k at small k does not spill because the heap fits in random access memory. For each query, predict whether DuckDB uses order by or top n, then verify with explain. Query 1, full sort, no limit. Query 2, sort with limit 10. Query 3, sort a varchar column with limit 100. Query 4, sort with a limit equal to the full row count. Write your predictions in O4 exercise.md before you run explain. Full sort, no limit, let me run explain. The scan reads all rows, no limit to bound the output. No limit means DuckDB must materialize the entire sorted result before returning row 1. The order by operator runs the full Radix sort. On 60 million rows, this will exhaust any reasonable memory limit and spill to disk. Limit 10. Let me check the operator. The scan still reads all 60 million rows, no index on L order key. With limit 10, DuckDB switches to top n. A 10-element heap is all that lives in memory. The scan feeds rows one by one. The heap keeps only the smallest 10 seen so far. No Radix sort, no spill. Varchar column, limit 100, same pattern. Same scan, all rows, no index path on L comment. Top n again. The key type is varchar here, not integer, but the operator shape is identical. The heap holds 100 elements and applies the same min-heap comparison logic using string ordering. The bounded heap cost is the same regardless of column type. Limit equal to the full row count, 60 million. The scan reads all rows as before. The limit is 60 million, equal to the full row count. DuckDB recognizes that a heap of 60 million entries is not cheaper than a sort and falls back to order by. The full Radix sort runs. A streaming limit sits above it to enforce the cap, but it passes through every sorted row since the limit matches the total. The same buffer pool that handles hash table spill in modules 05 manages sorted run pages here. Same mechanism, different operator. In modules 07, we'll see how zone maps can help sort queries skip row groups entirely, reducing the data that ever reaches the sort operator. Let's recap. Radix sort, 8 passes, O of n times k, no comparisons, only works for fixed width keys like int64. For varchar, DuckDB falls back to comparison-based sort. Two-phase sort, each thread builds more local sorted runs, then a k-way merge combines them. The buffer pool handles spill transparently. The sort operator never calls spill directly. Order by plus limit uses the top n operator. A heap of k per thread, O of k memory, never materializes all rows. No spill risk for small k. Next up, module 07, zone maps and row group pruning.